There we are. Is that okay for everyone?
Yes, Chris, thanks
Good.
very much.
Excellent, that's good. Okay, so living by the sea, how to survive and thrive in the maritime zone. I'm going to talk a lot about things that live in and around and by the sea or the coast. What I'm going to do not talk about really are animals. I'm going to talk about plants because we all know plants are brilliant. And animals are easy. Animals, by and large, when they're faced with environmental stresses, which may be especially difficult ones, variable in time over a period of months or over a period of hours even, such as on the coast, animals can just move, go up and move, bugger off, that's it. They don't have to suffer the slings and arrows of outrageous environmental stresses. But however, plants can't do that. Plants have to stand and stay wherever they are and cope with everything that's thrown at them. So the adaptations associated with plants are just so much more immense than the animals' adaptations, at least in my humble opinion. So that's what we're going to look at, is how to survive and thrive if you're a plant in the maritime zone. If we're looking at the environmental stresses by the coast, there's all sorts of them, but the main ones perhaps are saltiness, salinity, drought, sun, because there's not much shade on a sand dune or on a shingle bank, the wind, and energy, which can include, of course, waves and all sorts of other factors. And what we're going to look at primarily is those plants on salt marshes, dunes, shingle banks, and to some extent rocky foreshores, which may or may not be showing different adaptations to surviving and thriving where they happen to be. To take the examples of sand dunes and shingle banks, the main environmental stresses, the ones that plants have to cope with primarily, are drought, the instability of the sediment, insolation, the fact that the sun beats down, and abrasion, when the sand is blowing or the shingle is being thrown around by high waves. On a salt marsh, yes, salinity. Once again, salinity becomes the main factor, perhaps, together with the fact that on a salt marsh you're in the intertidal zone, so it's alternating exposure and inundation. So the variability throughout the day, throughout the monthly cycle, and throughout the annual cycles in terms of the stresses. And then moving on to the very end, the rocky shores, again, you have exposure and inundation being an issue, but also the added stress of wave damage. So all the plants that are living in these places have to be adapted to these stresses and arguably more. Adaptations can come in a whole range of forms. They can be structural, chemical, behavioral, and others as well. For example, evolutionary is one example of adaptations that I'm going to be covering towards the end. So the main adaptations listed up there in no particular order, and in many ways, some of those adaptations are actually come in different elements of those categories. But I suppose overall, the biggest thing that plants have to cope with by the coast is drought. But drought ain't just drought. Drought comes in two forms as well. Drought, in the easy to recognize sense, is you ain't got enough water. It's too dry, the ground's too freely draining, or something like that. But that's physical drought. But there's also physiological drought, which is where there's insufficient water, but it's insufficient of the right sort of water. Water everywhere, never a drop to drink. Most plants cannot easily cope with salt water. So for most plants, the coastal environment is a place where they have to tolerate salt water. Salt water tends to draw water out of the plants and create physiological drought. So we have these two forms of drought coming along and side by side on the coast, and a range of adaptations to try and deal with that. On this slide, perhaps the most obvious form of drought, particularly in the intertidal zone, is physiological drought. And one of the key ways of plants coping with that is the phenomenon of succulence. That is fleshiness, if you want it in English, succulence, as it's called botanically. And the glasswort is the prime example of a succulent plant growing in this sort of habitat, a salt marsh plant. Why should a plant grow like that, effectively looking a bit like a cactus without spines? Its stems are fleshy, its stems are cylindrical. And that's all for very good reason. The fleshiness of the stems, that is a reservoir. That's a reservoir where water, fresh water, when it falls upon the plant, can be stored for physiological use at times when it's not available. That fresh water can help to dilute the salt which inevitably gets into these plants. But by having a stem which is very rounded, the rounded stem per unit volume of the plant presents the smallest possible surface area to the environment, and it is of course surface area of the plant through which salt could be taken in when the tide comes in. So all of these features beautifully represented there in glasswort, but that's only one of many examples. Sea beet, top right, that is also succulent. One of the key things about sea beet is the fact that it's got very exciting, well, not very exciting, flowers, as you see to the left there. Sea beet is a member of the Chenopodiaceae, the spinach family, or as it should be known now, the Amaranthaceae. It's been subsumed into that by the recent version of Stace. Sea beet and glasswort are both in that family. And indeed, if you go anywhere in the world where the salt, from the Cheshire Salt Lakes through to the salt marshes of the Lincolnshire coast, through to the salt steppes of Kazakhstan, it will be members of the Chenopodiaceae, the spinach family, which are the predominant plants growing there. They have evolved the most incredible range of adaptations towards dealing with salt and the physiological drought it causes. Just a pity they haven't got more attractive flowers, I guess. But succulence isn't restricted only to members of this family. All sorts of plants growing by the coast, you can see there the sea mayweed, bottom right. That is exactly the same. It has succulent tissues. Its leaf segments are linear like the inland mayweeds, but if you cut them in cross-section rather than being flattened, they're rounded. Effectively, mini versions of the samphire leaves. They're rounded for the very same reason. Dealing with drought needs a whole set of other adaptations as well, given that succulence isn't always the right solution. There are all sorts of other things that plants have evolved in order to cope with the either physiological or physical drought. And leaf surface coatings and modifications are one of those. Many plants, like the sea kale, like the sea spurge, have waxy leaf coatings. That waxy leaf coating is a physical barrier to water loss from the plant. Of course, it's also whitish and therefore reflects the worst, perhaps the worst of the sun's energy. So you have one adaptation here, which is dealing with two potential stressors. Waxy coatings are one form of adaptation. Another form are the leaf surface coatings. Hairiness. You can see there very clearly, top right, the hairs on the leaves of yellow-horned poppy. Down below, the hairiness or the cottoniness on sea wormwood, and here on the bottom right, the most cottony of all, the cottonweed, sadly a species now extinct in the UK, but you never know, it may return. The yellow-horned poppy shows the leaves very well, but the hairs form a layer right across it, and the importance of those hairs is several-fold. First of all, they reflect sunlight. They help to keep the plant cool. But perhaps more importantly, the hairs trap a layer of air close to the leaf surface. On the leaf surface, there are the stomata, the breathing holes that allow carbon dioxide in for photosynthesis, but unfortunately, from the plant's point of view, in a droughty habitat, let water vapor out. By trapping a layer of semi-saturated air, semi-saturated with water vapor, close to the leaf surface, that reduces the gradient and reduces the loss of water from the plant to the environment. So these leaf coatings work in very precise and complementary ways in order to reduce the risk of the drought stresses. But the adaptations shown by plants are not just on the surface coatings. Sometimes it's much more detailed adaptations, such as the seed properties. Now, if you are a plant living, say, on shingle, such as the maritime curl dock, yellow-horned poppy, what you don't want is to have tiny seeds that disappear down between the pieces of shingle and never get seen again. They need to be close to the surface. And the maritime curled dock shows that very, very clearly. If you look at the seeds, here, the seeds have 3 swollen tubercles on the seeds. The inland variety of curled dock has just 1. So in effect, the overall seed size is 3 times larger on the maritime curled dock than it is on the inland curled dock. Yellow-horned poppy does have very tiny seeds, but it has very long seed pods, and a lot of its seeds are held within the seed pods when the seed pod is shed. So the seed pod lodges at the surface. Some seeds will be shed, they go to form a seed bank, but others will remain on the surface, and that leads to them being in the right place they need to be to germinate the following season. Having large seeds or large seed pods like that is one way. Another way is to add cork to those seeds. And sea kale, as you can see top right, does have large, corky seeds. Again, for size, but also, given that sea kale grows right down by the tide levels, it also, the corkiness is protecting the embryo against the salt of the environment. It also gives it a flotation device so that it can be carried by the currents in the maritime environment. So the corky seeds of sea kale are superbly adapted to living in its preferred habitat. Sea rocket, likewise, largish, corky seeds, or seed pods in this case, which are simply shed in their entirety, and as with sea kale, they're corky, they float, and they can then therefore survive, the embryos can survive the salt and survive the journey from the point at which they're shed to the point at which they're washed up by the sea currents. If we go underground, all sorts of other adaptations then come to the fore. And here you see several of those. These are to do with the roots and the runners. On the left-hand side of the screen, you have those species which have either very deep roots, such as sea bindweed, or deep and tap roots, swollen roots like sea holly and wild carrot. The purpose of having deep roots is to get down to the water table, because in any sand dune system, these being sand dune plants, in any sand dune system below the surface, often meters below, there will be freshwater lenses. And they will, if they can be accessed by the roots from the plants, then that plant can survive and thrive. Once it's got its water, ideally, it'll have somewhere to store it. So that's where the carrot-like taproots of the sea holly and the, as its name says, the carrot-like carrot roots, they're water storage as much as anything. They store the water within the taproot for times of stress. On the right-hand side, we have a rather different set of rooting type structures, roots and runners, which form three-dimensional foraging networks, as it were, foraging for the limited amounts of water in the sand. Sea sandwort, Honkinia, long, almost spaghetti-like runners, which forage along and can find any water that's available. Marram grass too, almost unlimited capacity to grow through sand, which is either depositing upon it or sideways through unstable sand. It can do that. It not only benefits itself by giving itself access to water, it also benefits the sand dune itself, because it stabilizes that sand dune, allows it to grow into the big structures that you can see to some extent in our part of the coastline on the east coast, but even better on the west coast, where sand dunes can grow to much larger magnitude, because the predominant winds are onshore, blowing sand onshore and allowing the sand to grow even further, stabilized by the roots in the three-dimensional skeleton of marram. Salt is one of the big problems, as we've said, and one of the approaches to dealing with salt, shown here by yet another member of the spinach family on the left-hand side, the sea purslane, is deciduousness. It loses its leaves, but it loses its leaves in winter after storing surplus salt that it's accumulated over the summer into them. This is a form of active secretion. We'll come back to sea purslane on a later slide because it shows so many different adaptations. But just to move on to the right-hand side, particularly on sand and shingle, the overall growth form of the plant is also important. And many plants grow in the form, like this sea campion, of a cushion where living material and dead material forms and acts as a sponge. That sponge can act to absorb water when it's available for use at times when it's not. The cushion-like growth also gives it resilience against the eternally windy conditions one tends to find on these coastlines. So it's not providing big interruptions to wind flow, and therefore it's not liable to be so badly damaged as more upright plants would be. But also related to this, the fact you have a lot of wind on these coasts is the fact that their plants, the plants have flowers which are, as I've termed, they're superfloral. They're larger than you might expect for the size of the plant itself. In this way, they're very similar to what you might think of as alpine plants. And of course, alpine plants, where it's cooler, seaside plants, where it's windier, both have a big problem of attracting sufficient pollinators. Hence the fact that one of the key characteristics of plants in both of those environments is flowers which are larger than the plant would seem to normally you'd normally expect on a plant of that particular size. Now, anything green on the sand dune or by the coast generally where it's droughty is obviously a sign to a herbivore that there's a nice healthy plant there. And that herbivore can not only get food from eating that plant, it can also get water. So an awful lot of the adaptations to thriving by the coast are actually anti-herbivore adaptations. These may range from, again, leaf structures, silveriness, downiness, spines, bristles, as we see on the left-hand side. It may be latex, as we see here with the sea spurge, toxic or semi-toxic substances which deter predators. That's herbivores. We don't have any of the ones that are quite as toxic as the sea squill, so characteristic around the Mediterranean. That one is so toxic that it can afford to live, as you see there, with its bulb sticking right out of the shallow soils, which, if it were not for the fact it's deadly poisonous, would be nibbled to fury with furious intensity by every browsing sheep and goat. So keeping things from eating you, again, is important when you're living and showing that you can survive in difficult, droughty conditions. Going down to the cellular and chemical level towards, as far as adaptations are concerned, returning on the left-hand side to the sea purslane. That is one that we've seen already. It is a plant which has many, many adaptations, but perhaps the most fascinating of all is that those little cells on the surface of the leaf are little desalination cells. So, whereas we have to, in the Middle East, build power stations to desalinate seawater, this plant can do it with little cells on its surface just under the power of its own steam. It can take in salt water when the tide's in. It can strip the salt out of that water, leaving fresh water behind for its own physiological use. And it can then excrete pure salt crystals through the surface of its leaves, and you can see these almost actively forming on a sunny day. Another cellular adaptation is shown also by sea spurge. We've just seen that one, and it's the same adaptation. It's the latex. The latex is a hygroscopic chemical which holds onto that water which is available. So a doubly functioning adaptation against herbivory and against direct drought. On the right-hand side, we have another suite of adaptations which are to do, chemical adaptations to do with the sun. Simple fact is that all of our coastal habitats don't have trees growing on them, or very few have trees growing on them. There's very little shade. Little shade means there's a lot of sunlight, and that high degree of insulation, often also added to by sunlight reflecting off pale sediments such as sand or gravel, can lead in extremis to sun damage. Hence the fact that it's quite common to find varieties of plants growing in these habitats which have sunscreen in them, anthocyanins. These are the reddish compounds laid down in the leaves of the herb robert or the sea beet there, or in the stems there of the woody nightshade or bittersweet. And these adaptations are simply there as sunscreen to prevent physiological or genetic damage to the plant as a result of excessive sunlight. There are many, many more adaptations as well, though. We've only just started to scratch the surface. On the left-hand side, you have the phoenix. These are all adaptations around life history of a plant. On the left-hand side, you have the plants which you could term as phoenix plants. They can simply dry up and still survive. Most higher plants simply can't do that. Most higher plants, if they dry up, if they wilt too far, they're dead. Lower plants such as mosses can do that. We tend not to find mosses in such dry areas, however. However, there are one or two, such as the sand screw moss, Tortula ruraliformis, which can simply dry itself out when drought is in action, and then as soon as the raindrop falls, you can actually watch the leaves unfurling as the plant springs back to life. That really rather gives the lie to the term that we often call mosses as lower plants. They're not lower in any sense at all. And in fact, you could probably think of them as higher plants. They've survived on the surface of the earth for a lot longer than these Johnny-come-latelys like the grasses. And moving on to the grasses, well, marram grass we've mentioned as having the long runners and three-dimensional rooting structures. Of course, marram is one of the textbook xerophytic species. That's plants which can cope with dry environments. And you see there the cross-section, which shows you what that adaptation is. All of the stomata of the marram grass are on the upper surface, that's the inside of that curled leaf. When it dries out, those green cells, which are particularly thin-walled, dry out preferentially before the rest of the cells of the leaf dry out, and that causes it to curl, fold up, such that the stomata are then opening only into a very small piece of the outside environment, which rapidly becomes filled with water vapor. And again, as with the hairs on the surface of the leaves earlier on, it allows them, it reduces the rate of further transpirational loss of water. Sand sedge on the right-hand side is another fascinating example. It's another one of these that one has runners, but it's one that has runners which are capable of foraging, actively foraging for what they want. Those runners, with the shoots coming up every 4 nodes, do branch occasionally. And when the runner, the particular part of the runner, finds itself in a piece of sand which is especially dry, it simply elongates the length between the shoots. It narrows the angle of branching and effectively sends the shoot shooting on into the distance, trying to find the habitat it actually wants to be in. So when it arrives in a relatively dry, a relatively damp area, what it then does think, right, that's great, I'm sorted now. So reduce the length of the internodes and increase the branching angle such that the number of shoots in the damper area is at a higher density than in the less favourable area. That is active, optimal foraging in plants. Most of the plants we've talked about at the moment, thus far, have been perennial plants. Not all, but most have been. Perennial plants do have to cope with things by being where they are right through several seasons. Another approach is to be an annual plant, and this is a way of dealing with variability in the stresses. We all know annual plants as being ones that grow quickly in your garden between the periods that you may turn the soil over. And something like Scarlet Pimpernel is a fantastic example of that, something that can go through its entire life cycle in a few weeks. But we have two separate subsets of annual plants which are particularly characteristic, again, of sand dunes. On sand dunes, the stressful period, the period of greatest stress for something on the body of a sand dune is the summer when it's droughty, whilst on the strand line, it's the winter when you have the between the equinoxes, the equinoctial gales, they're the time when the plant is most likely to be damaged. The being a summer annual, therefore, that is germinating after the spring equinox and doing your business by the time of the autumn equinox, means you can get away with the period of the year when tide and wave damage is least likely to be a feature. On the body of the sand dune, however, you have the period of greatest stress being the summer when the sand dries out the quickest and the most. So there, the annual strategy required is being a winter annual, germinate in the autumn, grow slowly through the winter such that in early spring you are at flowering size and you can get over undone with flowering usually by May, and your seeds can over summer as a relatively drought tolerant seed. In many ways you can think of that as being estivation. Often see snails estivating in the summer. When it gets too warm, they shut up shop. Well, think of the seeds of the winter annual plants as just the estivating structures, shutting up shop for the period of greatest stress, allowing them then to carry on the process in the autumn. Almost finally amongst the range of adaptations are the evolutionary adaptations. Now, anyone who knows a salt marsh knows glassworts. We've seen those. Anyone who knows a salt marsh knows that glassworts are incredibly variable. There are loads of different species and they are remarkably similar to look at. There are 3 or 4 different species in that photograph there, but essentially each one, the best identified actually in the autumn, when the autumn is distinctive autumn colour. Essentially, each one of those very closely related species is particularly well adapted to living in one zone of the salt marsh, and therefore several different species can grow side by side together. Some are adapted to growing in the lower salt marshes where they're covered by every tide, others in the upper salt marshes where they're covered by only the highest tides of the tidal cycle. That's where evolution has taken those species down to individual species. Within species, genetic differentiation also takes place, and you can see similar things with annual sea blight, but they're not species. Genetic work has shown that they're basically varieties of one species, the annual sea blight. So the different colour forms in this case are just varieties of one species, as indeed are the different flower forms of the sea aster. Very different looking, and often with a different zone on the shore, the rayed form of the sea aster typically being on the lower shores, and the rayless form, or the discoid form of the sea aster being on the upper shores, or the muddier inner shores in the estuary. I've just put in there a picture of sea lavenders as a taste of things perhaps to come, because common sea lavender is probably going to end up one of these days subdivided by some person who hasn't got anything better to do with their time in a PhD study into a whole range of other different clonal microspecies, as they've done with the rock sea lavenders. Because one can see in a picture like that, there are very different looking sea lavenders occupying any particular patch of salt marsh. They may well be different species, who knows? That's something for botanists of the future to worry about. Moving finally then onto the rocky shores, the zones there are rather different. because you have two zones of environmental stress on the rocky shores. You have environmental stresses of exposure. Lower down a rocky shore, it's exposed for less of the day than, or the tidal cycle, than the upper shore. Conversely, on the lower shore, it is more exposed to wave attack. And animals are the classic examples which distribute according to those zones. In the intertidal zone, where exposure becomes a problem, then you find things which either are covered in slime and therefore replicate the water experience even when there is no water there, such as the suckerfish, or you find things which can shut up shop by closing their holes, the barnacles, with plates or with operculum, as in the periwinkles, or indeed clamping themselves to the rocks, as in with the limpets. So these are all ones that have adapted to the exposure. These guys also adapted to the wave attack because they're covered in the hard shells. So looking at the plants on a rocky shore, and I know you haven't got many of those in Lincolnshire, neither have we down here in Essex, but they're always interesting to look at, starting at the lower shore on the bottom left, where exposure is least, but exposure to air is least, but exposure to waves is greatest. Large leathery species, such as the kelps, with big holdfasts, root-like structures, which hold them onto the rocks. Leathery leaves, and also with brown seaweeds typically covered with mucus, like the suckerfish, to replicate the marine the water environment. Moving right to the top of the rocky shore, you find the zone of the plants which again are the phoenix plants, the ones that can dry up again, particularly green seaweeds. They dry up totally if they need to, but can rehydrate quite happily when they get covered by water. The red seaweeds tend to form somewhere within the two extremes, although one red seaweed, the corallina, which has adapted to wave attack by depositing calcium carbonate upon its fronds, will go further down the shore than most other red seaweeds. Conversely, of course, also on the upper shore, one can find a single species of brown seaweed, Pelvicia canaliculata, which is has channels, as its name suggests, channel rack, channels in which water can remain when the tide's gone out. We talked about stresses. The sea is not all bad. There's lots of good things about the sea. And one of those is the fact that it's a giant storage heater. So things don't need to be so frost tolerant if they're living by the sea. Indeed, one can find by the sea several plants, many plants indeed, which are primarily plants of more southerly climes, but do come north protected by the warmth provided by the sea. And examples here are hog's fennel, which is a salt marsh and coastal plant, or coastal plant in Essex. But further south in Europe, it's found inland in limestone grasslands, for example. Likewise, Goldilocks aster, similar sort of distribution on a European scale. But here, on the limits of its range, here in Britain, it's very much a coastal species. The counterpart problem that gives, of course, is that the ameliorated environment by the coast can allow colonization by alien species from other parts of the world, warmer parts of the world. And here there is no family which is worth more of a problem than the Azoaceae, the Carpobrotus family, the Hottentot fig family, Mesembryanthemum family. Several species of those which are now increasingly invading our coastal strip, particularly in the southwest, such as here on the lizard. in encroaching upon the natural maritime vegetation and excluding native species almost totally. The other good thing about the sea is that it does have currents and tides and waves. Those are able to move structures around, move seeds around, particularly as we've seen with sea kale. So the plants living in these environments can colonize, and they do colonize. If you create a new salt marsh, you will see glassworts colonizing, brought in by the tide within the first year. Coastal plants do move around. We are seeing it all the time. The sea knotgrass, once restricted just a couple of localities on the south coast, has now spread along the south coast, probably partly due to climate change. This one hasn't reappeared as yet. That's purple spurge, is now extinct in the UK, but certainly it is expected that it could well recolonise, because of course colonisation by sea currents isn't just from this country, it can come from elsewhere too. And we may even have seen that already in Devon, where the sea daffodil has been discovered in one location. It's otherwise found only as far north as southern Brittany, but arguably that one could have colonised naturally thanks to the sea currents around our coastline. Very, very rapidly, if the plants are going to survive and thrive, yes, they've got to survive all the things that the environment can throw at it. They've also got to survive everything that we as a species throw at them. Pollution, overexploitation, such as bait digging, recreational pressures leading to erosion, exploitation of energy as well, in the form of wind farms. All of these can be anthropogenic stressors and can be predominant in one part of the coastline or another. Countrywide, until recently, the biggest problem was always deemed to be land claim. That is taking land from the sea for use by humans, whether it's for housing or industry or whatever, or agriculture even. That's the activity that used to be called reclamation. Reclamation, an activity which is called reclamation as a means of trying to give a degree of moral respectability to something which is always absolutely disastrous. But fortunately, that's largely died off now at the moment, given perhaps the next now greatest pressure, that is sea level rise, largely caused by global warming combined in places with landfall due to isostatic settling. The sea level rise is putting and climate breakdown are putting the coast under ever greater stress, putting the plants that live on the coast in ever greater stress. Hence, the creation of the principle of managed realignment, sustainable management of the coastline, to allow the sea to reclaim, that's the proper use of that term, reclaim the land that we've claimed from it in historic times. All of these are activities which take place on the coastline, but the fact that managed realignment does work actually says something. Unlike the gross disasters that are taking place elsewhere in the country, HS2, fantastic example of something where a development is going through ancient woodlands, left, right and centre, and the organisation doing it is saying, yes, we're compensating for that by planting few trees. Well, no, that is wrong. That is not possible. You cannot recreate 800 years of history and the ecological complexity of that 800 years of history. However, the coastline has a saving grace. It is always being reshaped under its own forces, being reshaped left, right and centre, and it changes on timescales which we can recognise, timescales which are not not out of kilter with our own conceptions of time. So Coastal habitats, because they are naturally created and recreated by nature, can indeed be encouraged to recreate by man, the saving grace, if there are any, of wildlife and conservation on the coast. And I think that's just about all I've got for you. I will take questions. Thank you for listening to me. As you can see on there, if you want any more on all of this, I can provide you with a couple of PDF publications, and I'm very happy to, if you want to contact me either directly or through Twitter or through my website for those PDFs, I'll happily send you them. But what I shall do is keep a mailing list of everyone who's asked for them, and when we've got something more substantial to printed to sell you, we'll be in touch. Thank you very much. I'll return the screen to Tammy, and thank you very much again.